Hi everyone! In this lecture video, we are going to talk about two of the most widely used materials in the world, which are the polymers and ceramics. At the end of this lecture video, first, you are expected to identify different natural and synthetic polymers and describe their composition. Second, you should be able to differentiate two types of polymer reaction, which are the addition and condensation polymerization. Third, you should realize the difference in formula of a monomer from that of a polymer and vice versa. Fourth, you should be able to learn how the structure of a polymer affects its properties. And lastly, you should be able to describe the different ceramic materials and its properties. For our first type of material, we have the polymer. Polymer from the two words poly means many and mer means units or number is a macromolecule which consists of many repeating units which are called monomers. Since polymer is a macromolecule or large long chain molecule, then we expect that it has a high molar mass that could reach more than 1,000,000 grams per mole. An example of a polymer is given in this figure. What we have here is a monomer called ethylene, which is characterized by carbon-carbon double band. If another identical ethylene molecule will attack the double band of this given monomer unit, they will eventually get connected in a covalent band to form the polymer polyethylene. So as we can see in the figure, polyethylene consists of many ethylene units. Polymers, however, can be categorized into two, depending on the type of monomers present in its structure. The first one is called homopolymer. This polymer contains only one type of monomer. The other one is called copolymer, which has two or more different monomers. Now let's try to go back and take a look at the brief history of the development of polymers. If you think about it, even before 2500 BC, polymers in terms of natural polymers have always existed and people have been using those for centuries and for thousands of years, like wood, cotton, and silk, which are used to make fabrics. Of course, we have natural rubber, which comes from the sap of a rubber tree, but it wasn't until 1800s that there was a sort of driving force to really use these materials and produce more of it efficiently. Well, the idea here is that all these natural materials have limited resources and non-sustainable, so efforts to make synthetic polymers were made by several scientists to address this problem. In early 1800s, rubber in particular began to see significant use, and natural rubber is not what we think of today, like rubber ball or tires that has a rigid kind of structure. This material before has a chewing gum-like properties, so there was a desire to try to improve those properties to make them more useful. And in 1844, Charles Goodyear found a way to create basically the rubber that we think of today that is more rigid and bouncy like a rubber ball. And this was a process that he discovered that he called vulcanization. And let me expound on this process later. In 1846, another gentleman by the name Christian Schnobein was able to synthesize an artificial polymer derived from cellulose, called nitrocellulose or gun cotton. His discovery began with an accident in his wife's kitchen. When he used her cotton apron to wipe up some spilled nitric and sulfuric acid, it disintegrated, leading to his work on nitrocellulose. Gun cotton, by the way, is employed in gunpowders and explosives. Another advancement were made in 1910 by a chemist named Leo Baekeland. He was credited with producing the first completely synthetic or man-made polymer called bakelite. This material found a lot of applications in things like kitchenwares and jewelries. And again, these were driven by the limitations of conventional materials. For example, before, the primary material that was used to produce billiard balls was ivory, the one from the tusk of an elephant. And obviously, that's a resource that's in limited supply. So there's a lot of interest to come up with alternatives, and bakelite was an example of the first commercial success of an effort to do that. Now, in 1919, one of the most important discovery was the idea that polymers are actually long-chain molecules held together by covalent bond. Before this year, that idea wasn't the view of these materials. People knew that yes, they are big molecules or macromolecules, but the conventional view was that they were just cluster or aggregates of molecules because it wasn't thought that there could be mechanism for these molecules to form long chains. This was such an important advancement and discovery such that Hermann Staudinger was awarded a Nobel Prize for this in 1953. And then here comes the year 1940, which was a major driver for the development of commercial polymer industries. During World War II, a shortage of several natural materials such as rubber and silk caused an intensive program to mass produce synthetic polymers. At that time, it was not just only all about discovering different kinds of new materials, but also it was all about finding ways to manufacture them intensively. Eventually, there comes a point wherein polymers or plastics actually surpass steel as the most widely used material. Now this time, we will start to enumerate different natural polymers and describe their composition. Generally, there are four natural polymers, and among them are the proteins. Proteins are polymers of amino acids. They play a key role in nearly all biological processes. Proteins also facilitate a wide range of functions, such as transport and storage of vital substances, coordinated motion, mechanical support, and protection against diseases. Major sources of proteins are meat, poultry, fish, eggs, dairy, beans, and nuts. Again, the basic structural units or monomer of a protein are amino acids. An amino acid contains at least one amino group, at least one carboxyl group, and a side group which is represented by R. Again, two or more similar or different amino acids will combine together to form the polymer protein in a condensation reaction producing water, which I will be discussing later on. There are 20 different amino acids that are building blocks of all the proteins in the human body. Among those are the ones shown in this table. We can see that the structure of this vital compound really do have three parts: the amino group, the carboxyl group, and the R group, which is the shaded green portion. These amino acids combine together in a covalent bond called peptide bond. The next type of natural polymers are the carbohydrates, which are generally defined as polymers of simple sugar or monosaccharide. Its major functions are for food storage and structural material. Sugars are classified as monosaccharide, disaccharide, and polysaccharide. Monosaccharide is the simplest form of sugar, such as fructose, which are mainly found in fruits. Disaccharide is a combination of two monosaccharide, such as sucrose, known as table sugar, which is formed from fructose and glucose. And then we have polysaccharide, which consists of more than two monosaccharide units. One example of a polysaccharide is cellulose, which is the main component of cotton, wood, and papers. It is composed of glucose monomers held together by a covalent bond called glycosidic bond. Another type of natural polymers are the nucleic acids. They have high molar masses that play an essential role in protein synthesis. DNA and RNA are the two types of nucleic acid. DNA molecules are among the largest molecules known. They have molar masses of up to tens of billions of grams. On the other hand, RNA molecules vary greatly in size, some having molar mass of about 25,000 grams. Both types of nucleic acid is made up of nucleotides, which are the monomers of nucleic acids. A simple nucleotide structure consists only of three major parts, as shown in the figure. It has a base part, which is a pair of purine and pyrimidine, a phosphate group, and sugars, which could either be deoxyribose for DNA or ribose for RNA. The moving figure shown in the right side is a DNA molecule having two strands of interconnected nucleotides which are linked together by hydrogen bonds. And then the last type of natural polymers is the polymer of isoprene, which is the natural rubber. This polymer comes from the sap of a rubber tree, where an aqueous suspension called latex, a milky white fluid, is produced through tapping. After collection of the tapped latex, rubber is recovered from emulsion by coagulation with formic acid, creating crumbs that resemble curds of milk. The figure below shows the structure of the rubber polymer, which is composed of repeating units of isoprene monomers. Let us now discuss how monomer molecules react together to form polymer chains. This process is basically called polymerization, which has two general types, the addition polymerization and the condensation polymerization. The first type of polymerization, which is the addition reaction, usually involves unsaturated compounds containing carbon-carbon double bonds or triple bonds. Consider the addition polymerization of the ethylene as shown in the figure. In this process, a free radical is required to initiate the reactions. The free radical would simply forms a bond to one of the carbon atoms in the double bond of the monomer, generating a new radical which will further react with another monomer and so on, producing the polymer polyethylene. With this, the process does not produce any molecular byproducts as the polymers incorporates all the reactant atoms in the final product. The other type of polymerization reaction is characterized by the release of a byproduct, which is usually in the form of water. One of the best known polymer condensation process is the reaction between hexamethylene diamine and adipic acid as shown in the figure below. The final product is called nylon 66 because there are 6 carbon atoms each in hexamethylene diamine and adipic acid. Before we proceed to the next topic, let me briefly go back first to the process which I've mentioned earlier, which is vulcanization. Again, this chemical process was discovered by Charles Goodyear. So he found that if you take a natural rubber and add sulfur and heat it up, it improves the mechanical properties of the natural rubber. And what was really happening was a process called cross-linking, as shown in the figure below. Natural rubber without vulcanization would lose most of its elasticity when strong external force is applied into it, as the individual chains would easily slip past one another. Now, because of cross-linking, the rubber material cannot now be easily ruptured because of the presence of this sulfur that holds together these individual chains. So the presence of sulfur would somehow restrict any strong deformation of the material, thus improving its strength. This vulcanization process paved the way for many practical and commercial uses of rubber, such as in automobile tires and dentures. Okay, at this point, let's begin to relate the structure of polymers to its physical properties. First, let's talk about the chain length, which is the first factor that attributes to the property of a polymer. We can express chain length in terms of the degree of polymerization, which is the number of repeated monomer units in the chain, and the molecular weight, which is the total molar mass. In general, the longer the chains yield higher strength and higher melting point. Another attribute to the physical property of polymers is the type of side group present in a given monomer. And in general, polar side groups containing monomer has stronger attraction between polymer chains and therefore has a higher strength. Hence, in this given table, the polymer of aspartic acid and asparagine have the highest strength as they have the most polar side chains. Another aspect of the molecular structure that affects the polymer property is crystallinity. This deals with how densely the polymer chains can be packed into space. So here, we are talking about how polymer chain folds into an arrangement that creates something close to a lattice, as shown in this ordered structure indicated by the red region. The general key concept here is the more intact or compact the chains, the stronger the polymer, while the less ordered or the more random the chain, as indicated by the blue region, the more flexible the polymer. The next factor affecting polymer mechanical property is branching. Branching restricts the chain from being able to compact and densely enough to crystallize, thus reducing its strength. So to have a clearer picture on this concept, let's say you're wearing a big backpack and you want to enter a crowded room where you keep bumping into people. So you can't really arrange fold into an ordered arrangement like in a crystal lattice because you need some space for the side group to fit on between these gaps. And then we have cross-linking, which I have already discussed in the previous slide about vulcanization. So again, cross-linking is basically holding polymer chains together. Here, there are some molecules that will hold polymer chains which would resist any deformation caused by some external forces. In general, cross-linking increases the strength of the polymer. Another way to classify different kinds of polymers is how they behave or respond to changes in surrounding environment. And we're going to talk about particularly their response with respect to changes in temperature. We can classify these polymers as either thermoplastics or thermosets. Thermoplastics become soft and glow at high temperatures and then hardened when they're cooled down to low temperatures. Thermosets, on the other hand, are rigid and they become set or cured at high temperatures, and then they remain solid for the rest of the time. So in other words, for thermoplastics, you can reheat to remelt it and cool it down again, and it will harden again, and you can do this procedure multiple times. A thermoset is not able to do that because once it becomes set at high temperatures, it remains that way. So when you heat it up again, it will start to decompose. Examples of thermoplastics are polyethylene, polystyrene, and polyvinyl chloride. On the other hand, examples of thermosets are vulcanized rubber and bakelite. All these examples are synthetic polymers, and this is going to be our topic of interest for the next following slides. At this portion of this lecture video, let's familiarize ourselves with the different synthetic polymers. These are materials that we can see around us almost every day. Again, with the limited resource of natural polymers, efforts to mimic these materials in the laboratory were made for sustainability. However, the widespread use of these synthetic polymers are also now kind of detrimental properties in the sense that they don't really break down very easily when they're disposed. Meaning, waste from these materials start to accumulate as they're thrown away. And so with this, people were interested in coming up with ways to degrade or break these materials to be reused and recycled. Now, to easily recycle these materials, the science community had came up with a system to easily identify these materials for efficient segregation. And this is the resin identification system. In this system, different types of polymer resin or plastics are coded with numbers 1 to 7 to easily sort them for recycling. Now the table here shows code numbers of plastic with their corresponding polymer identity with acronyms and their corresponding monomer. So in the next slide, we'll talk about each of these type of synthetic polymers. Code number 1 corresponds to polyethylene terephthalate or PETE. PETE having a brand name Dacron is the most common thermoplastic material of the polyester family. PETE is a condensation polymer made from the monomers of ethylene glycol and terephthalic acid. It is used as fibers for clothing and containers for liquids and food because it is resistant to attack by microorganisms and does not biologically degrade. It is ideal to only use them one time and should not be heated as this could leach antimony, which is toxic to human, and phthalate, which is regarded as one of the most dangerous pollutants. Code number 2 is for high density polyethylene or HDPE. HDPE is an addition linear chain polymer made from ethylene. Now, since the polymer chain of this material is linear, meaning it has no branches, so folding arrangement, which is a characteristic of a crystalline material, is possible. Hence, this material has a high strength. That's why this polymer is famous for its tensile strength and resistant to high temperatures. So as we can see in this image, the sample materials for HDPE are rigid. That's why they can also be used to manufacture furniture like plastic chairs. Code 3 is for polyvinyl chloride or PVC. PVC is an addition polymer made from vinyl chloride monomers. Main uses of PVC is for pipes and floor tile. PVCs are lightweight and when added with plasticizer, it can form flexible materials such as shower curtains and garden hose. However, the use of PVC is decreasing in popularity because of the serious health and environmental pollution issues associated with its manufacture. And then code 4 is for LDPE or low density polyethylene. This polymer is also made up of ethylene monomers in addition reaction, same with HDPE. The difference between these two is that the polymer chain of LDPE already has branches unlike HDPE, which is only linear. And of course, we know the effect of this branching. So we expect that LDPE has low strength and melting point. And because of that, they're not good structural materials. LDPE is found in many flexible materials such as wash bottle, disposable plastic cups, and packaging films such as sandwich bags. However, they are not really a good food packing materials because though they are resistant to moisture, they are poor oxygen barrier and they are susceptible to heat. And with that, foods spoil quickly. Now we have code 5, which is for polypropylene. Polypropylene is an addition polymer made from propylene monomers. It has high heat resistance and does not absorb water. Therefore, they're good for food packaging such as cup for instant noodles and yogurt containers. Code 6 is for polystyrene, which is an addition polymer made from styrene monomers. They are widely used in the food service industry. Items like coffee cups, meal packaging are often polystyrene, or more commonly known as styrofoam. However, this material is toxic due to possible leaching of benzene when in contact with hot and oily food. This benzene is a known human carcinogen. That's why if you had noticed, fast food chains such as Jollibee and McDonald's, they do not longer use styrofoam as their packaging container for their combo meals. What they are using now are those hard paper-like materials. And then lastly, we have code 7, which is for other resins or plastics. This category includes many other polymers other than the 6 previously specified. Examples include nylon and polycarbonate, and combinations or blends of different polymers. Usually, polymers are being blended to improve mechanical property or strength of the materials. So things such as 3 to 5 gallon water bottles, bulletproof materials, DVDs, computer cases are items that fall under this category. Now let me add more examples of other polymers that are considered as major discovery. The first one is polytetrafluoroethylene or Teflon. This is an addition polymer made up of tetrafluoroethylene monomers. It is hydrophobic and has high heat resistance. That's why its main use is as coating material of non-stick frying pan and other cookware. Second, we have synthetic rubber. Now, this is different from the vulcanized natural rubber because here, the raw materials are completely all synthetic. Synthetic rubbers are called elastomers, which are made from petroleum products such as ethylene, propylene, and butadiene. One example of an elastomer is neoprene, which is the first synthetic rubber, which is an additional polymer formed from chloroprene monomers. Neoprene is the most famously used in wetsuits, like in scuba diving or in surfing, and this material keeps you warm in water. And then lastly, we have nylon, which is the trade name for a polyimide material which is made from a condensation reaction between hexamethylene diamine and adipic acid. Nylon have found significant commercial applications in fabric. Nylon became the major go-to alternative for the limited resource of silk. Other nylon materials are the nylon bristled toothbrush, women's stockings, and ropes. And for our last topic, we will be briefly talking about another widely used material different from polymers, and these are the ceramics. Ceramics comes from the Greek word keramikos, meaning burnt stuff or pottery. Ceramics are inorganic non-metallic materials that are shaped and hardened at high temperatures. Ceramics are compounds or combination of compounds wherein atoms are held together by either ionic bond or covalent bond, such as alumina, magnesia, silica, silicon trinitride, and mullite. The most commonly known ceramics are glass, cement, tiles, porcelain, and bricks. So just like any other materials, ceramics also exhibit different characteristics. They are hard, brittle, meaning they break easily. They also do not react readily in contact with other substances. That means they are inert. They are wear resistant. That means they do not get easily damaged by friction. They have refractory properties, so they are resistant to decomposition by heat. They have poor electrical and thermal conductivity, and they are not attracted by a magnetic field. And that ends our lecture video. I hope you learned a lot of things from this. Thank you for watching. Goodbye.